Hello. Hello, Animesh. Great. So we can start now. I don't know where Animesh is. Yeah. So we are starting. Sure. Let's talk about. Great. Okay. So did anyone try yesterday what we tried to cover? And if anybody did try, are there any problems? Did you face something which you should not, or which was okay? So somebody did try it. That's good. So did you face any problems, or was it smooth? I tried. So let's see what today's agenda is. Okay, great. So today we are going to cover a few things. First thing, what we are going to cover today is the limitation of LD payload based rootkits. Then after that, we will see, as we talked in the first uh, session, that the another method to develop rootkits on Linux in user mode is ptrace, right? So then we will see how ptrace works. Getting familiar with the ptrace would be exploring its options, how it works, why does it work that way. Then what we will do is we will inject a shell code with ptrace, I mean using ptrace into a process. So what that would do is we will that will achieve the same result, but I mean we already did shellcode injection yesterday, right? We injected a shellcode, but that was through function hooking. We can also do function hooking, but in this session we are not going to try the function hooking part. Instead, the session is going to be more about ptrace and less about how to use it in the function hooking and other things. Is that clear? Okay, so let's start this thing. So what is the limitation of LD payload based rootkits? So as we have seen already, LD payload based rootkits don't work on a few things. The first thing is, well, they don't work on statically compiled binaries. Though the number of statically compiled binaries is uh, almost more or less non-existent, or should not be considered, because almost any binary that you are going to see is going to be most probably a dynamically compiled binary. But again, there are some things that do not cover stuff, right? Then second thing is, I mean, we have ptrace. So ptrace is a more complete approach for this thing. So through LD payload, we essentially develop a library and we just load it before any other libraries. So it is more of a trick thing and less of an actual, you know, object or thing to use with. What ptrace is the actual thing that is supposed to provide the tracing or controlling things. So ptrace is not developed to control softwares or other things. Ptrace has been developed to aid in debugging. So the GDB or any other debugger on the Linux systems basically use ptrace. So ptrace provides you the ability to control binaries, to debug it, to see the data, to modify the data or the text section or virtual memory registers, or basically anything. So ptrace is basically in a single line, if we are going to say what ptrace is a debugger in of itself. So to achieve various things, for example, first you are trying to, let's suppose you want to debug a software, but you also want the listing of applications code or data, or you want to see what is the data at a particular location. So every single thing is achieved using the single ptrace function, man ptrace function or system call, right? So this is the sys ptrace, and the first thing that we pass it is a request, right, which is an enum. And if we scroll down, we see there are a lot of options: trace me, peak text, peak data, peak user, poke text, poke data, poke user, get registers, get f registers, fp registers, right, get reg set. So basically we can do almost anything. We can set signal mask, we can set options, we can remove options, uh, we can get registers, like what the values of registers at a certain instance in a process's execution state, as well as we can set the or modify the register. So basically we control almost anything if we are tracing a program using or a process using ptrace, right? But there is a little problem, right? So just because ptrace is this powerful, you are not really allowed to use ptrace by default. So we have something by the name yum. So let me show you, right? So there we go. So it basically restricts processes or system or user to use ptrace by default. So since ptrace is generally used as a troubleshooting tool, or the gdb also uses ptrace, so the kernel is by default supposed to not allow to use ptrace on any system. So what you have to do is you have to basically disable it. So let's see what the current status is. Oh, sorry, that did not work. That should work. So this is set to 1. We need to set it to 0. So these are the various options. 0 means all processes can be debugged as long as they are the same UID. So that is the basically what you would expect uh, it to work this way, because um, since you are since you are the user and you have a particular UID, as well as, so you basically have control over all the processes with the same UID which have been launched by the user that you are, right? So ptrace scope 1 is only a parent process can be debugged. Only the parent process can debug, right? So what happens is when ptrace scope 1 is set, without, if you don't want to modify this thing and set it to 0, so that you might want to mitigate something that they are trying to mitigate, what you can do is you can create a process and then fork it, so it also creates a child process, and then you debug the child process from the same process. Or if you don't want to go through that much hassle, what you can do is you can just switch it off or set the setting to 1. I mean, set the setting to 0, and then you can debug almost any process. And of course, being a user, you cannot debug root processes or anything, so that thing is still there. So any questions till now? Okay, great. So what we're going to do is, first we are going to see this thing in actions, project speedtrace, right? So okay, just save it. Okay, so this is, let's see, so inject. So the first thing that we're going to see is a ptrace.c program, which basically creates a child using fork, as we talk about, right? So without disabling the policy, we can still have a little look, and the child invokes the ptrace with trace me, so that it can issue that it is allowed to be traced by its parent. And what we do is we just execute a bin ls. So this demo code has been taken from internet just to use as a little demo, right? Then what we have is child with PID. We are printing what is the child's PID. We are waiting for the notification or the signal from the child. And then what we do is we issue the ptrace with peak user option, or the peak user request type. So what the peak user request type tells is the current state of, not really the not really all of the registers, but it tells a specific registers value at the certain point in time, right? So this should, since we are going to use uh, exec based system call, and exec v is what, 59 in on a 64-bit system. So this should give us 59. Yeah, 59 is the syscall exec v. If you remember, if you don't remember, we can see it this way. And as you see, exec v system call number is 59. And since a child process, since we are here inside the child, it is calling exec, a variant of exec. So C library provides multiple exec variants to be used, right? This is how, but again, so it is one of the multiple features that ptrace provides you. Any questions?
No, sir.
Okay, great. So what we're going to do now is we are going to disable that protection, and let's just set it to 0 so we can debug, or we can basically inject arbitrary shellcode into arbitrary processes, which would be one of the various tasks that you would want to achieve, right? So let's create, I think I have the program, proc.c. Yeah, so we have this program, proc.c, which just says I'm running and it waits for the input, right? So gcc, it is proc.c. Yep, demo proc, and let's just do demo proc. And what we did not do is to change the protection back to 0, right? Process kernel. Yep, and it is 0, so we can do anything. Let's just say ps. Yeah, and the process id is this 5386. So let's move to another process, which is, this is the program. So this is the same shellcode that I was using yesterday. With it is a bind shell which binds at 4444, and it is taken from this link. So if you want to have the same shellcode, you can just retrieve this shellcode from here, right? And this is another shellcode which I was testing again, but yeah. So this is the main program. Okay, yeah. So what we are doing here is, okay, first we take the child's PID as the argument, and then we attach it with the ptrace attach request type. So what this does is it will attach to that PID, child PID, right? Though it is not child, it's just a variable name I took here, right? Now, if ptrace fails, it returns a -1. So we always check whether the uh, syscall failed or passed, right? We are waiting for it to get attached and notify us via signal. Here we go. First, we get the registers. So get regs gets the registers at that particular point in time, and argument it requires is this: a pointer to a struct reg struct. And if we see this structure, right, this is the reg struct. As you can see, since we are on a 64-bit system, it has all the general purpose registers of a 64-bit, right? R15 to R8, and then RX, RCX, RDX, RSI, RDI, original rex, RIPCS, eflex. So basically it has all the registers. So when we do this get res with the parameter, so what it does is it fills this register structure with the values. Okay, so I was also trying to use the capstone disassembly engine, so as to display what is inside the memory, but let's not complicate things right now. Okay, So what we do is we are printing the original RIP, then we are injecting the code. So we have a shellcode mine. Where is shellcode mine? Yeah, so this is the shellcode. So the shellcode mine is the shellcode which is the bind shellcode. And we are going to inject it inside the processes space, and we will resume the execution. So let's see how it works. Okay, not list ptrace2, and the PID it requires is this 5386. Let's also see whether netstat is showing something. Nope. There we go. And here we have this shell code executed inside the processes memory space. Now let's see whether it works on statically compiled binaries or not. And let's just exit it. Control C. GCC minus static. Yep. Five, 6, 2, 4. Nothing here. 5, 6, 2, 4. And it is what it is. And here, even in a statically compiled binary, we are able to inject our shell code. So this is one of the advantage that you have over LDP load based rootkits, that you can basically control anything and everything, whether the binary is dynamically compiled or dynamically linking based compilation, how you would want to call that thing, or the binary is statically compiled. So any questions? What does return 1, 2, and 3 mean? Return 1, 2, 3, and return 1, 2, and 3 mean nothing. It's just okay. So let's see. Okay, well, by the way, I have written return 2 twice. So what happens is, let's suppose we are using this, right? And we are just, since the ptrace does not, ptrace did not finish, and I just want to, get out of the program, just terminate the program. So return from main would do the task. Now, I also need to figure out where the return failed, or I mean, where the program failed. So these return 1, 2, 3, and 4. I mean, I've written it twice, so let's just fix it. Right, the first one should be return 1, the second one would be return 2, third one would be return 3, and the fourth one would be return 4. So what happens is, let's suppose I'm not able to attach to the process, right? So I'll show you how it works. Okay, netstat, it is still working. Let's just try to connect to it. 1, 2, 3, 4, ls, and our shellcode runs, right? Exit. Let's just exit it, and here we go. There, the program executed properly. And even if we run it again, we can see that the program was not changed actually. So what happened was, there were no modification inside the actual binary. It was all in the runtime process space. So this gives another advantage, that the file on the disk is actually not being modified. So again, the signature is same, every single thing is same. We are just manipulating stuff in the memory. So okay, now let's see if we have a process. So these are root processes, and let's see if I want to connect to this process, right? Or if I want to uh, ptrace this process. And of course, the ptrace should fail, right? ptrace2, and there we go. Failed to get the child process, and the return was 2. Oh, just because I did not compile that thing. gcc ptrace2.c minus o ptrace. Okay, minus l capstone. Yeah, see, failed to get the child process. And if I check what was the return status, it tells 2. Wait, why does it says 2? Okay, there was some problem with this thing, but yeah, so that should not be the problem. It should return a proper return status. But it is still saying the failed to get the child process, so we are pretty sure that it is failing here, and of course it would fail here because ptrace cannot attach to a root process when you are a normal user, so you cannot attach to a process. If condition is twice, that's why. Which condition are you talking about? No, the ptrace, what ptrace returns is when you ask for it memory. For example, you want to read a block of memory from a certain point, it returns that memory. Else, when it is this kind of statement, wait, where is it twice? It's the same thing. Yeah, let it be. So the point is, this block, if it fails somewhere before this, it should return 1. If it fails before this, it should return 2. If it fails at this point, well, the first 2 has passed, so it will return 3. So what it does is, most of the times, or almost every time, it allows me to see exactly which statement failed. So this that. Okay, any more questions? I don't think there are any other questions. Okay, so let's see. So let's see how we are able to perform the code injection part. So first this is just for the show to be more or less to see whether we are able to get the registers or not. Now, as well as we are printing, if you see, okay, it is also printing the RIP of that process at that point in time. Now let's see what happens next. So we are calling inject data with the shell code as a parameter, the child PID, and the current RIP. So what the basic idea of this injection is, that we are the RIP, since RIP is in text section and the RIP points to the next statement to get executed, we are writing memory, or we are writing a shell code directly in the text section, basically overwriting other instructions of the process which are there. And therefore, when the process continues, when we detach the process using ptrace detach, so what happens is the debugging portion is detached and the process continues as it should continue, right, without stopping again and again and again under the influence of debugger or anything. So this is how it works. First we attach to the process, then we get the registers, because we need to have the location where we have to write the instructions, and since these are executable instructions, it makes sense to write them in the text section. But how would you figure out where uh, are those instructions getting written to? Because at the end of the day, if you do not know where the instructions are getting written to, I mean, the first thing is you also need to specify where to write. But again, if you don't know, how will you set the RIP to that location? So instead, what you do is you take the value of RIP by first calling ptrace with getRes functionality. So it returns all the registers. And after that, you use the value of current RIP in the target process, or current EIP in the target process if we are talking about 32-bit systems. So we use that location to write a shellcode to. And once that has been done, we set it again. We set the RIP back to its original location and just continue execution. So that, and I think you get the point, right? How to write a shellcode. Won't this injection crash the target process? Yes, this injection can crash the target process, and this injection might not crash the target process. The point is, it makes sense to try stuff, right? I mean, once the shellcode is finished, what will happen? The process will simply crash. Yes, this current piece of code is so bad that of course this will crash it. But to write a code which is not going to crash it, you might have to do some other task as well. For example, let's say what would be the what would be the better approach of injecting a shellcode? Is there any way to so the target class does not crash? Yes, we are discussing that right now. So another thing that can be done is you might want to inject it, let's suppose, at some location before the RIP, before the current RIP. So what that would do is, well, since that code has already been executed and then you move it back to that location, you might skip that crash part. But of course, that might again crash because the next code might depend on the previous code's state. And this is the actual problem with using ptrace. So you can modify the state of the program, but you also need to take care about, you also need to restore that state again back to its previous state, or else the program will crash definitely. Now another thing, let's say, is what else can we do? The thing is, I don't think we can inject it in a code. I mean, we should be able to create a new thread and inject it there and and execute the thread, but that is a little too much of you know I would say effort. So in the next scenario, in the next demo, what we're going to see is we will see how to inject a custom um, code, or basically a shell code, but not a actually working shell code. What we're going to attempt is to make the attached process a syscall that we want. So what that will achieve is it should be able to do anything. Now, okay, is there a way? Now I have another solution for that. What you can do is you can inject a DLL, sorry, not a DLL, a shared object inside the process's target space. So the shared object, once that loads, it can execute itself. So that can be done, but I would say take that as a homework if you are really interested in doing that thing. Now, another thing that I'm going to do is I'm going to release a list of blog posts on these sessions and everything that I cover here. So later, though I have not written even the first blog post yet, it might take about a week or two to write the blog post. So in case you want to, see things again, and I might add a few examples over there as well. So you might want to see that thing. But right now, I have not written anything which does not crash the process using ptrace, and you will see it in the next scenario. I mean, how it is this hard to do stuff, right? So any other questions? Yeah, I think I can we can move now. There are no other questions. So let's see what happens if we try to how to inject shared object. Yes, injecting a shared object is one of the things that we will attempt right now. Right? We are not going to attempt the injection of shared object, but what we are going to do is we will, yes, said we can inject shared object and that will not. Actually, you said we can inject shared object and that will not crash process. That will crash process. It is the same thing as injecting a shell code and not crashing the process. It depends on you how you are writing the code so that so that your injection does not crash the process. Ptrace by default is not going to crash your process, and neither will it force you to not crash it. So the way you write the code, the way you inject something in the target process, it is entirely up to you. So just because you are injecting or you are trying to inject a shared object does not mean the process will not crash. The process will crash if you modify the state to such a point that it cannot execute further. And we will see this thing, right? So This is one thing. Inject. So let's see what happens if we try to inject something, or if we try to make it return a system call or do a system call. Let's see what happens if, see if there are any system calls for injecting libraries. Yeah. Unfortunately, there is no system call to perform a DL open or DL. Yeah, so DL open is the function call. If we see, so DL open is a call to open a shared object, but this is not a system call. So what you have, what you would have to do is you would have to first figure out something. I would say first figure out the glibc's base address where glibc is mapped, and from there you would see where DL open is. You can calculate the offsets based upon the versions of glibc, then add that offset, then you move to DL open. But there are these pointers. The file name would be your malicious or non-malicious, just for the testing purposes, shared object, and the flags, and then you would just call it with the desired options. But again, you would have to write this at least this thing inside the process's target space. So yeah, it really takes a lot of time and effort to move around. Another problematic part is it is the ptrace is not really that much documented. So most of the time you are like wondering why it is not working or not. You will see that in a minute. I think you get the gist of how you can inject a custom shared object inside a process's memory using ptrace. Okay, moving ahead. So yeah, so this is the next program. So no, this is the next program. So what it does is it just takes the victim PID and it calls inject into victim PID, right? And let's just see what we are here having, right? So this is the function inject into. This function is the entry point for the code injection here, and that more or less we are going to perform every single thing inside this function, or this function is going to call every single other function that we would ever want to do perform inside a process's memory using ptrace, right? So let's see. First, it tries to get the ptrace, then it gets the registers. After getting the registers, what it does is it calls do cool stuff with PID and registers, and then once that cool stuff has been done, it just detaches it so that the victim process can continue its execution after its state has been modified, right? So let's see what do cool stuff does. So this is the do cool stuff function, and as you can see, it is quite long. I mean, it's quite big, right? So yeah. So what this function does is, right now, what I'm calling is just just make the victim process execute the right syscall with this string to be printed. So this is what I'm trying to achieve, and let's see if we can do that thing. So first things first, let's see whether we have this ptrace to inject. So we have inject, and it requires the PID. Let's run our process, demo proc, and let's just do the inject with demo proc. The PID is 6038. So 6038. Ptrace status is -1 for some reason. Yeah, so but as you see, the process already made this syscall pawned by Himanshu Khokhar Jaat. But what happened is after a certain point, it crashed. Well, actually, the process crashed. Let's try to investigate what happened using strace and notless demo proc. And let's say another other idea. This is the demo proc's PID 6076 and 6076. And we cannot attach to it because strace is already debugging it. So it is already under attach. So it is already attached to some other parent process. Now when you attach to something, the process becomes the parent process of that thing, and since s executed it, s is by default the parent process of this thing. So we cannot see what happens now, but yeah. Other thing that can be done is,
So,
yes,
correct. You said stress has become the parent process.
yes, s was the parent process here.
So, can't we attach that stress and start means 6073 PID?
Well, that would mean that we are injecting into s, but yeah, let's see what happens. I mean, this is more of the thing that I'm doing right now, and I have not done this previously to be shown in the demo. And there we go. It did this, and here we go. See, this is what it crashed. The s crashed.
So we can't figure out like how why did it? We
Yeah,
can't
let's
investigate.
more or less, I would say, let's have a look at the program, and you will see, you will understand the complexity. So we are first we have declared another another user register structure, so that we copy the value what we obtained from get registers, and once we have performed the system call, we just set them back, right? So here it is. Then it's just peak text, and these are the old bytes. Wait a second, old RIP. I think I'm doing the wrong thing. Yeah, okay, so what I'm doing is from the RIP, or from the next instruction, I am reading 4 bytes because my jump here is of 4 bytes. It's actually syscall instruction, syscalls opcodes. So this is syscall, and since syscall is 2 bytes in machine language, so what we have is 2 knobs to just make it 4 bytes, right? Alignment, more or less. You can say that thing. So we are taking the old 4 bytes, and what we do is we are saving those 4 bytes. And the next thing we are going to do is we are going to write those new syscall at that point, and then we will set the register. So in effect, what this will do is, since we are going to write the syscall instruction at the RIP in the target process, after the syscall finishes, we need to write the previous data back, so that the process can return to its original state, more or less, you can say. So that is what was attempted here, but for some reason, say, it sets up the right one. This is the right syscall. Right has the uh, syscall number 1. 1 is for the standard output, then the pointer to the string that we want to print, which is wait which is this string. And then what we do is, there it is. Yeah, so there is the length, so how many bytes to write. So this is what the write requires: the syscall number, the output fd stream where to write it, then the location of the string, and the length, about how many bytes to write. And once we do that, write syscall, we just write that there with the, and then we set the registers, we continue the process, and after that, after continuation, what we do is we again copy back. So I really believe there is something that I'm doing wrong, but the point is we are able to make the syscall set, syscall right here. And if we see it in the process, let's just for the proper display part, let's just add a new line right here, so that makes it look much better. And let's just, the length would be, yeah, the length is the same, so really no need to fix anything. Hmm. 6256. So 6256. There we go. And here it is properly. Right, syscall. So this is more or less how you would go about executing, uh, you know, process, or this is how you would go about controlling the target's process memory using strays. And now this is where stuff gets interesting. So the question was, if we return to our previous question, how to inject a shared object. So the shared object injection would be more like, you need to figure out where the glibc is located, then you need to figure out the offset. Well, you can obviously calculate the offset of any function within the glibc, but then you need to, do add that to get to the process, then you fix the parameters and then you call that. So this is not really more on the fly approach. You would really need to first obtain where the glibc is located, and when you are trying to figure out the glibc is located, that one approach would be to read the maps file from the process proc. As you can see, get proc self maps. So this is, if we see, this is where the glibc is mapped, right? So there you can try to read this file, and then from there you can try to figure out where the functions are located. You would need to figure out where dl open is located, and then what you will do is, in case of dl open, uh, the file or the shared object that you are going to load it, what you are going to do is, in that shared object you will just set the attribute as the constructor. So if you're familiar with what constructors are in the C++ or any object-oriented language, the C compiler also provides you a GNU, I would say, attribute of constructor. So that attribute, when you specify the attribute, the function acts as a constructor, and the moment library gets loaded inside the process memory, the constructor fires and it executes your code. But maintaining the state of the process is one of the things that needs to look into, because you might be unknowingly crashing some things, or some syscall. For example, you are doing a syscall and it might have some unnecessary side effects on another registers or on any other state of the program. So that is one of the things that you really need to take care of in, if you are working with ptrace. But this is the exactly same thing that we did not need to worry about when we were developing ldp load based things. And this is precisely the reason, if you go about finding about linux rootkits, almost every single rootkit you will find on github or any attack, if it is a linux user mode rootkit, it is using ldp load, just because it is super easy to work with, right? I think you get the what I'm trying to say. So any questions till this point?
Explain the last one, LDP, something you were saying. Please, could you explain that?
Sorry, I was saying what? I did not
Sir,
get you.
you were saying something about LDP. It is the better process. I couldn't get it, sir.
Yeah, so what I'm saying is, since this takes so much time to work with, we yesterday and the day before yesterday, when we were having our ldp load based demos, we saw that it is far easier to create an ldp preload based rootkit. So let's see what is the uh, let's see the code for uh, so this was the code for super advanced.c, which just hooks string compare and executes the shellcode. And this is the point. The most of the code is to just mmap it and actually mprotect to just change the permission and nothing else. It's just create a function pointer, copy the code, and just get it done with. And what we did was, there was one.c which was you know bypassing or hiding our files. Hiding would be the better option. So it was hiding our files. And this is the basic code. You just call the next, you just call the original function, check whether the name contains the magic prefix or not, and just, if it is, just call the next again. It was the simple. But in case of ptrace, if we come here, even just the task of calling the right syscall is this hard. So, and even after writing so much code, because you have to check at every instance, and even after writing so much code, you are just like uh, it crashes. So in terms of functionality, ptrace is not limited if we are talking about functionality. So ptrace is something that can do almost anything you would ever want to do, but the point is it comes with the cost of usability. So it is not really that usable if you want to. So one of the examples that I want to show you of the ptrace is, yeah, see this. So this is the user.h file which you need to include it, which includes the definition or declaration of structures and the registers structure, the fpu registers, and then structure of the user part and everything, right? And if you see it, the whole purpose of this file is for gdb and gdb only. Don't read too much into it. Don't use it for anything other than gdb unless you know what you're doing. So this is what I'm talking about. The support is more or less just for the GDB purposes. You are not really encouraged to, you are actually discouraged from doing anything other than that. Don't read too much for it, and the purpose is for GDB only. So you're not really encouraged to use btrace, and this is one of the reason that things are not documented. Things are not documented, so more or less you are only limited to what man page says and what you can find on internet. But again, so now another thing that I would say is, let's suppose you are going to create a syscall, or you are going to make the syscall. So let's come to this thing, and what we are here is we are manually setting the registers. We are saving the state. Okay, here we are saving the old register state, and after that what we are doing is we are again reviving the old state, and then we are writing that back again to the process, right? So this, in ld preload based things, you don't have to do this much. You don't have to do any of this thing. You just hook the function and you just write the code you want to execute, and that's it. So this explains why there are almost zero, very limited. You can even count them on fingers if there are that much rootkits on Linux which are ptrace based. This was what I was saying. So this is the actual limitation of ptrace. So this ptrace is the problem. This is the actual problematic part of the ptrace. And I believe more or less we have covered stuff what we wanted to cover today. So any questions?
Sir, can't we read the binary code which is present in that process memory?
Yes, we can read that binary code present in that process memory.
Like how? So, what I'm trying to achieve is, if you can read the binary, no, binary ahead that RIP,
Yes,
what we can do is like append that binary to our shell code,
yes,
then inject it. Then it will replace the entire rest of the binary,
yes.
and then
Okay,
then also there
so
is a possibility
see,
it will crash or something.
yes, first there is the definite possibility that it will crash, and the second thing is it is not really feasible because let me show you the problem with this approach, right? So no, cd projects. Now let's say we are trying to inject into demo pro, right? So let's just take it to the top, ls minus lh demo pro, right? So this file is of 843 kbs. It's a static binary. Let's just compile it again as a not static binary, right? So as a dynamic binary, this is where we are. So you have 17 kb of data inside the binary. The text section is of course not 17 kb as such, but let's suppose the text section is what, 5 kbs in size. And this is just the file that just says, let's review the code, right? What does it say? And inject demo proc is the file proc, yeah. So it just says printf and get care. It just waits for the output so that we can inject it into it. Let's suppose we are working on a big binary. So talking about this case, we have, let's suppose we have about 5 kbs of text section. And when we are attaching to it, first we need to figure out how much has already executed. Let's suppose 1 kb has already executed, right? Out of 5 kbs of text section. So we have 4 kbs of text section. Now, we have our shell code, and if we are going to append that 4 kb to our shell code, which can be done, so we have to overwrite literally the 4 kb or the rest of the text section, which you can understand is not really that feasible, because the feasibility again comes at the cost of how ptrace works. So let me show you how ptrace writes data, right? So the peak the peak text is when it reads a word from the address in memory, and poc text is it copies the word data. So word is the word size. So in 32-bit system it is 32 bits, or is 4 bytes. In 64-bit system it is 8 bytes. So first let's see how many bytes. So we have about 4 kbs. 4 into 1024. Yeah, I mean that is bytes. So we have 4096, and let's divide it by 4096 by 8. 4096 divided by 8. Sorry, 4096. So we will need to call ptrace at least 512 times to rewrite the text section again, and we also have to write our shell code. So let's add 20 more calls to ptrace. Let's say the size is 150 or 160, or let's say something of more than 100 bytes in size for the shell code that we are using. So we are going to make about 550 syscalls just to rewrite the text section of this file. So you do understand that there are problems, right? Another thing that would be is the state. For example, it was in a state, and the next instruction we just added our shell code to that thing, and then we rewrote the whole text section. So that would place is, let's suppose there was this, okay, node gedit text. So let's see a little introduction to assembly language. So let's suppose there was like compare ex with 5, then test ex, yeah, let's just subtract it. Subtract ex ebx, test ex with ex again. First we see whether ex is 0 or not, and then if it is, jump f0 on next label, or else just continue something. Let's just say there are like 3 no constructions and there's nothing. So the problem is, let's suppose we break here. Let's just suppose, right? So, or might be here. So this jz depends upon the flag, whether the 0 flag is set. 0 flag is set or not. It will dictate the next instruction. And here, let's suppose we inserted our shell code, because more or less, if we are just going to put the shell code at the RIP, which we talked about, why we are going to insert the shell code at RIP, this is where we are going to, this is where it goes. So now, first thing, it depends on the 0 flag, whether it is set or not by our shell code. Now, of course, when we saving the state, we can revive the state, but reviving the state also means reviving the eflags register, which has the 0 flag, whether it was set or not. But then there is a next problem. So JZ is like jump to the next location. So what I'm saying is this code, or maybe this is the next label here, right? So So what I'm saying is this code or this code might have a dependence on this and the previous states that was executed by before our shell code. And this is where the actual complexity is. First thing, we just cannot append the whole text section to our shell code, because there, let's suppose there were shell code is 50 instructions, right? So if we do not append it, we overwrite those 50 and therefore corrupt the state. To preserve the state, if we just copy every single thing, then again the same problem comes. We just cannot copy every single thing. We just cannot do anything. So this is why it uh, takes as much effort in planning, as much effort to get it done actually. So writing the ptrace code is one thing, organizing how you have to write it is a different thing. So I think that is clear why we cannot do that task of just appending every single thing after we have done the shell code, right?
Okay, sir.
Hmm.
Uh, how to read binary any data like
How to read data?
no how to read that binary or something if we want.
If you want, you would have to just call the, oh yeah, I forgot, you also need to call ptrace about this many times at least to read whole of the data. And of course you also need to have that much space in your program so that you can write that again. So
Yes.
to read that data, yeah, here it is, right? So you call the ptrace with peak data. Peak text or peak data are interchangeable. So what it does is, when you call ptrace with peak text or peak data, then the PID of the process where you want to read it, this is the location and this is null, right? This is the location and this is null. So this is what happens is you read that here. Okay, I think I know the reason. It should be end of old EIP. Yeah, I will have to see and I will just update the code if I figure out where the problem is. So peak text and peak data return the the data. This is the peak data. So returns a word at the address in the traces memory, right? So address is the third parameter, which is the pointer. Yeah, okay, so that does not need to be a pointer because that is already the RIP. And since this is already RIP and we want to read from RIP the current instruction or the current 4 bytes, it will return it. But the problem is, again, it will return a word. This is where we are, peak text. It returns a word. A word is again 4 bytes or 8 bytes in size. So at best you are able to just read a word, nothing more. So to read a big block of data, you need to run this instruction in a loop with constantly updating the old RIP. I mean the where from where you want to read the data or the instructions from, if you are reading from the text section. And to write something at the text section or anywhere in the process memory, you call now here, yeah, it is here. So you call poc text or poc data. So peak text or peak data is to read, is for reading, and poc text or poc data is for writing the data inside the processor's address space. So is that clear?
Yes, sir. Sir, is it possible, like some one process
Hmm.
is suppose executing a loop
Yeah.
for suppose 150 times
Huh.
random.
Huh.
Now I want that using ptrace uh, to override that 100 with some other like
Some other value, let's say 20 or
uh,
let's say 2000, right?
yes, yes. So is
Yes, you
it
can do that provided you know the exact this thing, exact address where that 100 or 150 is located, so you can override that thing. So you can read that with with peak text and you can override that with poc text. So yes, as long as you know the address and you know exactly what is to write, you can do that thing.
okay?
But first,
Yeah.
the thing would be to figure out where that instruction is located, right? In
Okay.
case of pi based binary, that would be different. In case of non pi binary, that would be different. So these additional constraints are what complex the already complex process.
Okay, sir.
Yeah. So any other questions? No, I think we have covered everything. And okay, so this was the today's session, more or less. I know it was kind of a mess, but again, Ptrace is a mess in itself, so can't really say anything. Now, what you can do is, if you are interested in doing Ptrace based stuff, you can explore more. You can see more options again through the main page is the only thing that will help you in figuring out which uh, I would say which option or which Ptrace request does what. And the trial and error is another approach that you would have to take, which thing works, which things do not work. And if something does not work and you cannot find it on internet or in the Mac page, then you are on your own. So I believe we have covered every single thing. Animesh? Okay, I don't think anybody is here. So we are all done.
Himanshu,
Yes.
so shall we just wind up for today?
Yeah, let's just wind up.
Yeah, because I guess even Animesh is offline, and no, I guess no doubts have
Came.
came up so far.
I just
Hmm.
came. I just came.
Welcome, Animesh.
Sorry.
Okay, so today's session has
Uh,
been completed, and just please wrap it up.
Okay, sure. So we're not wrapping up this one here, and actually, I'm getting some updates for upcoming sessions.
Hmm.
Just wait 1 second.
Okay, what is your doubt? Someone by the
Not
name, nahi, tera nahi. Someone by the name Galaxy A6 Plus says he has a doubt.
okay.
Okay, I think he is typing. Let's see what he says.
okay, maybe in private.
Yeah,
Yeah.
that is in private.
Hmm.
Okay. So we are having a talk on mobile application development using Flutter. So if anyone interested to join, please have a look on our website. It will be updated within 1.5 hours. So this is one talk, and another one we are scheduling for digital forensics. It will be on Friday. So we have two talks coming up. Tomorrow we have sessions with Mushraji. That will be the same one with malware, part 3. You can tune up for that one as well. And we had something related to web applications. We are working on the same part as well for web application pen testing. If you find something, we'll look into that one as well. And anything else? Anyone like you
Okay, so
want us to
let's
talk?
just yeah. So just a second, let me clear his doubt. So the what is the disadvantages of Ptrace? Well, we went through every single thing. What are the disadvantages of Ptrace? Ptrace is inherently not encouraged to work with. So you are not encouraged to use Ptrace in your applications. You are not encouraged to read or to make sense of the header files or anything that are being used by Ptrace. It is specifically says that the files are to be used for GDB and GDB only. Again, at the very least, if you don't know what you're doing, just don't do it because you will crash. At the very least, one or two things. And the last thing is, it really requires you to have the complete understanding of computer application states, registers, memory, almost anything that goes on behind the scenes of how or when a process executes, what happens behind the scenes, how process context switching is done, how to preserve registers, how not to preserve registers, how to properly overwrite data or not corrupt any other thing at the same time, right? You would want to execute your shell code, but at the same time you do not want the process to crash. So, and this is a big problem. This is why these are some of the disadvantages of ptrace. So I think we are clear with that thing, right?
Okay, so we are getting hit around 8 to 10. Awesome. So actually, I got one question. Let me check this one out quickly.
Hmm.
Going to be keep Google. So what he said. Okay, so this is from some people. Aditya Naresh.
Okay.
Something on ROP chains as well.
What's something on ROP chains as well? So the question is for you or me?
I think it's for us actually.
Yes, I
He
believe
wants
so.
something on ROP, but I have no idea what to do with that thing. Okay,
So
we'll look for.
ROP is, I believe we are all familiar with that thing, that ROP is one of the concepts in exploit development. So we might be able to cover, anybody who is going to cover exploit development should or would be the person who is going to cover ROP, rope chains, and what are they, how to use them, how to create your own rope chains, what to look for, how to make them location independent, basically bypassing ASLR and stuff. We have not yet planned what or when we are going to cover exploit development, so can't really say about the ROP chains part. But in case we are having the exploit development sessions, yes, we will try to cover rope chains. I think that should be.
Yeah, that should work properly. Okay, so thank you guys for joining us. And you said we can inject as shared object. I think you already gone with this question.
Yeah, I.
When?
Yeah.
Okay. So I got another one. Okay, Flutter one. It's not updated. Well, I'm going to update all those things, so don't be worried. You'll getting emails based on those things. So yeah, thank you guys for joining in, and we'll see you tomorrow. And have a nice time. So I'm gonna stop sharing on YouTube first because last